In this video, we're going to take a look at microreactions. So if early in the chapter, we know that the product of an aldol condensation is an alpha-beta unsaturated carbonyl. So I have my carbonyl group, and then the alpha and beta position, the double bond is between those two carbons. If I look at the resonance structures for these alpha-beta unsaturated carbonyl groups, I can move the lone pair up onto the oxygen, giving me a carbocation and a negative charge on the oxygen. I now have an allylic carbocation, so I can move the pi bond over, putting the carbocation on the beta position. And so in these alpha-beta unsaturated carbonyls, we have two electrophilic positions. We have the carbon connected to the oxygen, and then the beta carbon is also electrophilic. And so either one of these carbons can be attacked by a nucleophile. Which one is going to be attacked depends on the strength of the nucleophile. Okay, so the stronger the nucleophile, the more reactive the nucleophile, the more likely we are to attack the carbonyl position. The weaker the nucleophile, the more likely we are to attack the beta position. And so if we compare Grignard reagents to Gilman reagents, we know that the Grignards are stronger nucleophiles. They're more reactive. And so when I react a Grignard reagent with this alpha-beta unsaturated carbonyl group, it's going to add the alkyl group onto the carbonyl carbon. The Gilman reagents are less reactive. They're not as strong a nucleophile as the Grignard reagents, and so they're more likely to attack the beta position. So when I react this compound with a Gilman's reagent, we attach the alkyl group to the beta position. When we attack the carbonyl carbon, we call that 1,2 addition because we're adding two atoms that are next to each other. So the carbonyl and the oxygen were added to. In the case of attacking the beta position, we call this 1,4 addition. It may look like we're attacking the we're adding across the double bond, but that's not the case. And so we're going to see on the next slide what the mechanism of this is and why we call this 1, 2, 3, 4 addition. Okay, so here's the mechanism of the 1,4 or the conjugate addition. And we'll see why we call it 1,4 addition as opposed to being 1,2. So from the last slide, right, this is our starting material, and we're imagining the nucleophile now is something like the Gilman's reagent, and this is our final product. We added the nucleophile here, and it looks like we added across the double bond, right? In fact, what's happening, when we attack with a nucleophile, we end up moving the pi bond over, and the lone pair goes up onto the oxygen. So we've added the nucleophile, and then now the oxygen is negatively charged, and so it's what is being attacked by the hydrogen from the acid. And so, in fact, we added to the 1, 2, 3, 4 positions. And so this is why it's called 1,4 or the conjugate addition, because we didn't directly add across a double bond, we added to 1, 2, 3, 4. We added to 1 and 4. Now, the reason this isn't the final product is because we have an enol. And so we know that enols will readily tautomerize to form the aldehyde or the ketone. And so when that happens, we end up with this as the final product. All right, so as we mentioned on the previous slides, strong nucleophiles tend to give us 1,2 addition, whereas weaker nucleophiles tend to give us the 1,4 or the conjugate addition. And so typical enolates are in the middle in terms of reactivity. And when I talk about a typical enolate, what I mean is right, if I imagine this ketone and I deprotonate it and remove that hydrogen, right, I can stabilize that enolate by drawing this resonance structure where the negative charge is on, I can spread it out onto that oxygen atom. So regular or singly stabilized enolates are sort of in the middle in terms of reactivity. They're not strong enough nucleophiles to get exclusively 1,2 addition. They're not weak enough nucleophiles to give us 1,4 addition. However, if I have a doubly stabilized enolet, right, so now if I imagine deprotonating this hydrogen, I could spread that negative charge onto both of these oxygens. Right? And remember, more stable means less reactive. So the fact that having this enolet would be doubly stabilized makes it weak enough that it's going to give me exclusively 1,4 addition. And so if I react this compound with potassium hydroxide, it's going to deprotonate this hydrogen, giving me the enolet, and then that enolet is going to attack here and give me exclusively 1,4 addition, and it's going to give me this product. And so this is an example of a Michael reaction. All right, so when we have a reaction between a nucleophile and an alpha-beta unsaturated carbonyl group, when we get only 1,4 addition, this is called a Michael reaction. And the nucleophile that does the conjugate addition, in this case the doubly stabilized enolet, is called the Michael donor because it's donating the electron pair. And then the alpha-beta unsaturated carbonyl group is called the Michael acceptor because it's accepting the lone pair of electrons when that nucleophile does its attacking. And so there are a number of different Michael donors that will give exclusively 1,4 addition with an unsaturated carbonyl compound. And so all of these are examples of Michael donors, and many of them are very similar. We have sort of doubly stabilized enolets or things that look like that. So we could have double ketones, double esters, a ketone and an ester mixed. We could have a nitrile along with a ketone, even though this isn't a carbon-oxygen double bond. We have the carbon-nitrogen double bond, which has a lot of similar properties. We saw that the Gilman's reagent gives exclusively 1,4 addition, and so it's included in the list of Michael donors. And then with the nitro group being so electron withdrawing, that especially stabilizes this negative charge, and so this also acts as a Michael donor. The Michael acceptors are all pretty similar. For the most part, they're alpha-beta unsaturated carbonyl compounds, whether they be aldehydes, ketones, esters, amides. We know that esters, amides, and nitriles are all carboxylic acid reducers, so it may not be surprising to see the nitrile listed here. And then the NO2 is kind of the oddball. I don't have a carbon-oxygen double bond, but I've got this nitrogen-oxygen double bond. But this having a double bond next to a nitro group is also considered a good Michael acceptor. All right, so I want to finish up this video by looking at several examples. So here I have an alpha-beta unsaturated carbonyl compound. Here I'm attacking it with a Grignard reagent. Now, the Grignard we know falls in the category of a very strong nucleophile, and so it's going to give us 1,2 addition, and it's going to attack at the carbonyl carbon. And so my product in this case is I'm going to add that ethyl group, and this is what I would sort of think of as a typical Grignard reaction. When I take a ketone, react it with a Grignard, I'm going to reduce it to an alcohol, and I'm going to add that R group. Now, when I have an alpha-beta unsaturated carbonyl compound and I react it with a Gilman's reagent, now I'm going to get the 1,4 addition. And so we're going to add the ethyl group to the beta carbon. And so my product in this case is going to be that. All right, so in this example, we want to predict the major product and draw the mechanism for the following steps. So I'm going to be reacting this diketone with potassium hydroxide. That's going to deprotonate the hydrogen here, giving me a doubly stabilized enolet. So this is going to give me a Michael addition. It's going to give me 1,4 or conjugate addition. And so I'm going to add this Michael donor to the beta position of this alpha-beta unsaturated carbonyl compound. And then with the acid workup, I'll get the final compound. So my product will be that. Now the mechanism is going to take a little bit more work. So the first thing I need to do is react this with hydroxide to give me the enolate. Now that's going to attack my alpha-beta unsaturated carbonyl compound. Then we'll hit this with H3O+. And I forgot my double bond, right? So I'm sorry to go back. In this step here, I should have put a double bond here and here to give me the enolate. And so now under acidic conditions, I need to tautomerize this to give me the ketone. And I have the resonance structure. And then deprotonate to get my final product. Okay, in this last example, I want to identify the Michael donor and the Michael acceptor that could be used to prepare the following compound in a Michael reaction. And so at first, it looks like there's a lot going on here. And so it's kind of hard to decide where this Michael reaction occurred. What was the new bond that I formed? But let's take a look at our list of Michael donors and Michael acceptors again. I think in these types of problems, the easiest thing to do is try to identify the Michael donor. Because what that's going to involve is the carbon that did the attacking is going to be sandwiched in between two carbonyl groups or something related, like this nitrile. or it could be a Gilman's reagent. That's maybe going to be easier because there's going to be less functional groups going on. We're just going to be, in this case, at the beta position relative to the carbonyl compound is where the alkyl group would have been added. But either we're looking for an NO2, and so the carbon next to that, or most of the Michael donors that we're looking at have the carbon sandwiched between two carbonyl groups, or replace one of the carbonyl groups with a nitrile. And so if I go back to the problem, I'm looking for sort of two neighboring carbonyl groups or a nitrile, right, that essentially have one carbon in between them. And so this is the pattern that I'm looking for, right? I have a carbon sandwiched in between our carbonyl group, and this could either be another carbonyl group, or in this case, it's the nitrile. So this is the carbon from my Michael donor that was the that had the lone pair. And then that makes sense because this is the beta position relative to this carbonyl compound. So this was my alpha beta unsaturated carbonyl compound, and this had the double bond that would have been here. So to figure out my Michael donor and my Michael acceptor, I just need to break this bond, and then this is my Michael donor, and this is my Michael acceptor. So that would be my Michael donor. And that guy is my Michael acceptor.